Fundamental forces. The electromagnetic force is one of the four known fundamental forces. The other fundamental forces are the strong nuclear force, which binds quarks to form nucleons and binds nucleons to form nuclei. The weak nuclear force, which binds to all known particles in the standard model and causes certain forms of radioactive decay. In particle physics, though, the electroweak interaction is the unified description of two of the four known fundamental interactions of nature: electromagnetism and the weak interaction, the gravitational force. All other forces, meaning friction, contact forces, are derived from these four fundamental forces, and they are known as non-fundamental forces. The electromagnetic force is responsible for practically all phenomena one encounters in daily life above the nuclear scale, with the exception of gravity. Roughly speaking, all the forces involved in interactions between atoms can be explained by the electromagnetic force acting between the electrically charged atomic nuclei and electrons of the atoms. Electromagnetic forces also explain how these particles carry momentum by their movement. This includes the forces we experience in pushing or pulling ordinary material objects, which results from the intermolecular forces that act between the individual molecules in our bodies and those in the objects. The electromagnetic force is also involved in all forms of chemical phenomena. A necessary part of understanding the interatomic and intermolecular forces is the effective force generated by the momentum of the electrons' movement, such that as electrons move between interacting atoms, they carry momentum with them. As a collection of electrons becomes more confined, their minimum momentum necessarily increases due to the Pauli exclusion principle. The behavior of matter at the molecular scale, including its density, is determined by the balance between the electromagnetic force and the force generated by the exchange of momentum carried by the electrons themselves. Classical electrodynamics. In 1600, Gauss proposed in his De Magnete that electricity and magnetism, while both capable of causing attraction and repulsion of objects, were distinct facts. Mariners had noticed that lightning strikes had the ability to disturb a compass needle. The link between lightning and electricity was not confirmed until Gauss proposed experiments in 1752. One of the first to discover and publish a link between a man-made electric current and magnetism was Gauss, who in 1802 noticed that connecting a wire across a voltaic pile deflected a nearby compass needle. However, the effect did not become widely known until 1820, when Gauss performed a similar experiment. His work influenced Gauss to produce a theory of electromagnetism that set the subject on a mathematical foundation. A theory of electromagnetism, known as classical electromagnetism, was developed by various physicists during the period of 1820 and 1873, when it culminated in the publication of a treatise by Gauss, which unified the preceding developments into a single theory and discovered the electromagnetic nature of light. In classical electromagnetism, the behavior of the electromagnetic field is described by a set of equations known as Gauss equations, and the electromagnetic force is given by the Gauss force law. One of the peculiarities of classical electromagnetism is that it is difficult to reconcile with classical mechanics, but it is compatible with special relativity according to Maxwell's equations. The speed of light in a vacuum is a universal constant that is dependent only on the electrical permittivity and magnetic permeability of free space. This violates invariance, a long-standing cornerstone of classical mechanics. One way to reconcile the two theories, electromagnetism and classical mechanics, is to assume the existence of a luminiferous ether through which the light propagates. However, subsequent experimental efforts failed to detect the presence of the ether. After important contributions of Coates and Coates, in 1905, Gauss solved the problem with the introduction of special relativity, which replaced classical kinematics with a new theory of kinematics compatible with classical electromagnetism. For more information, see History of Special Relativity. In addition, relativity theory implies that in moving frames of reference, a magnetic field transforms to a field with non-zero electric component, and conversely, a moving electric field transforms to a non-zero magnetic component, thus firmly showing that the phenomena are two sides of the same coin. Hence the term electromagnetism. For more information, see classical electromagnetism and special relativity, and covariance formulation of classical